In this video, I'm going to take a look at doing a t-test in Jamovi. We're doing an independent t-test, but we will take a look at both the versions of it, I guess the regular version and the Welch's version if you've got unequal variances. So we're using a t-test when we have two independent groups. And in this case, we have people trying to estimate how long 10 seconds is, which is our time estimate. And each person estimated once under the condition of eyes open or eyes closed. So they're two separate groups. If they were paired measurements, they would be going across the rows. So if you have just 1 and a 2 for the eyes open and eyes closed, you can go into the data tab and set up, and you can just rename them there. You can see the codes are still here, but I just typed in some labels. So 1 was eyes open and 2 was eyes closed, if everyone followed the instructions, which they may not have, which is fine. So usually the first thing we want to do is take a look at our data. So let's do a box plot first and just see if there's anything unusual going on. That will be under the exploration tab. And there may be some options to do the graphs under the t-tests too. We'll see that when we get to it. I've only had a quick play around with it. So we're interested in the time estimate and we're splitting by condition. I'm not so much interested in this table here, but I do kind of wish that the default was across the rows. I'm not sure why the default is down the columns. I feel like this is a more usual way of formatting this type of summary. So if we take a look at the summary here, the eyes open estimate was 9.8 seconds and the eyes closed was 10.16. So that's pretty close. So we're, at this stage, I'm not really expecting any difference, but let's have a look at the box plot. So we can see that there are some outliers with the eyes closed, which is interesting. So I don't know if that was, and they're the longer time estimates. I don't know if people were drifting off with their eyes closed. If you have a situation like this, in general, I leave the outliers in unless we've got a good reason to exclude them. But if you're concerned that they're having an impact on the test, you can run the test twice and you can say, this is what we got with the outliers. If we exclude the outliers, then we get this. And then that would maybe help you draw an informed conclusion. But in general, you can't just delete data because it's messy. If this is an accurate representation of what happens when people have their eyes closed and they're estimating time, then we kind of need to know that. So I will leave them in. I'm just wondering what the histogram does. Oh, it does give us the two histograms. Nice. So the histograms are, I guess, nice for looking at the shape, perhaps the symmetry, but the outliers aren't marked quite as clearly. Like this one is probably fairly obvious, but I do find that the box plots are better for looking at the outliers. And if you do have some asymmetry, then the box plots are also helpful because you can sort of see what's happening with where the median is. And we could put the mean on there too. And the width of the box and the tails. So it might be interesting to see how much these outliers are pulling on the mean. So the outliers will have the effect of pulling the mean away from the median. So it's possible that if you removed these outliers, this mean would sort of spring right back to the median there. So they are having an effect. I'm just not convinced it's a big effect. But anyway, let's run the test. So if we go over to t-tests and we have separate groups, so that means it's an independent samples t-test. And we probably don't need to have our data open anymore. So I'll leave that there just so I'm not standing in front of the commands. So our time estimate is the dependent variable. It's the thing that we're testing to see if it depends on the condition. Also our outcome variable or our, I've lost my words, all the other words that we use for dependent variables. There's usually more words for independent variables actually than dependent ones. Response was the other word I was looking for, response variable. And our grouping variable, which is our independent variable, explanatory variable, predictive variable, experimental factor, lots of names we could give that one. Our grouping variable is condition, and that was the eyes open or closed. So it's going to run the test straight away for us, which is nice, and there's no evidence of a difference between the groups. However, It is giving us a warning that there is a violation of the assumption of equal variances, and we can run this test. So if we click on the homogeneity test, this is talking about homogeneity of variances. So homo means the same, so this is the same variance test. This is using Levine's test of variances. In class, we did just a basic F test, and you might also see Bartlett's test. It's a little bit frustrating when you're learning statistics that there's always several ways to do something, because many statisticians come up with slightly different ways of doing stuff which are slightly more correct for particular circumstances or more robust. Anyway, so the null hypothesis is that the variances are equal. We have a small p-value, well, relatively small. So we've got evidence against the null hypothesis, and we will conclude that the variances are not equal. And honestly, that's mostly because of these outliers, I should think, but that's fine. So if the variances are not equal, we can run the Welch's t-test. And what that does is a slightly different version of the t-test, which is less sensitive to unequal variances. Most of the time you get the same result. So you'll see the p-value has changed a little bit. I think I can even put a pointer up. Let's do that. So the regular t-test gave us a p-value of 0.44 if we're rounding, and then the extra version for unequal variances gives us a p-value of 0.45. So it's a very small difference. So this tends to only matter if you have small sample sizes, very unequal variances. Most of the time, your regular t-test is pretty robust and it's going to hold up fairly well. But if you want to be the most correct and you have unequal variances, then you should use Welch's t-test. If there is a really severe problem and it doesn't make sense to test the means at all, then we can actually test the distributional shape or the medians. We can test something different, and that's why this man Whitney U is here. So this actually works by ranking all the observations, and it's testing the mean rank. And if you rank everything rather than using the raw observations, then the outliers are no longer outliers. So that is something that you can do in that situation, but we're not covering it. So the other thing that we can tick off in Jamovi is we can change the alternative if we want to. In most cases, you're just going to want the two-sided alternative. You can do a normality test if you want to. In general, I wouldn't bother. The data looked fine. The t-test is pretty robust, even if there is a very small honestly, sometimes even if there's a large problem with the normality, it's not going to matter because of the central limit theorem. So I don't feel that this is too important. And we can also get some additional statistics out. So we're not going to cover effect sizes in this subject, but you might in a later one. But we could look at the mean difference and the confidence interval for the difference between the groups. Now, in this case, there actually wasn't much of a difference between the groups, not a significant difference anyway. So this confidence interval, I'm going to expect that it will cover 0, and this mean difference will be somewhere around 0. So if we tick that off and ask for the confidence interval, it's telling us that the mean difference between the groups is 0.36 of a second. So it's a very small difference. And this confidence interval goes from negative 1.2 seconds to plus 0.5 seconds. So it's around 0. So it's telling us that the true difference between the two conditions, eyes open or eyes closed, when you're estimating 10 seconds, could just be 0. So this confidence interval will line up with the p-value. So if the p-value tells you that there is no significant difference between the groups, the confidence interval for that difference will include 0. At the 95 and 5% level. So if you're using 5% as a cutoff and doing 95% confidence intervals, they'll line up. Okay, so I think that's it for an independent samples t-test. If you have any questions or any trouble, please post to the forum or put a comment on the video, and then in the next video I'll take a look at the chi-squared test.